Let us talk about solving ordinary differential equations with homogeneous functions. A homogeneous function is a function that satisfies the following property. F of tx, ty is the same as t to the power n f of x, y. The order of the homogeneity is said to be n in this case. So let's apply this to solving a concrete problem. Let's try solving y prime equals y squared plus x squared over xy. Now this problem may not initially be stated like this. You could have got the problem as follows. You could have been given the problem as solve y prime equals y squared plus x squared or something like that. And then you have to take it upon yourself to recognize that this is a homogeneous function of order 2 in this case. So you'll have to divide both sides by xy to proceed. And why is it a homogeneous function of order 2? Let us see if it satisfies the test. This is f of xy. So f of tx, ty in this case is going to be t squared y squared plus t squared x squared over tx ty. So I should say that the order of homogeneity, if it's 0, the function is said to be simply homogeneous. So if the order is 0, it's homogeneous. So this is going to be t squared over t squared times f of xy. So that's going to be t to the power 0 f of xy, and that means the order is 0, which means the function is homogeneous. A homogeneous function is very good to have because we can solve it by a very simple procedure, and that is to divide both sides by x squared in this case. So I'm going to get y prime equals y squared over x squared plus 1 over y over x. This method does assume that x squared is not 0, and you have to keep this in mind because if the solution comes out with x squared not equal to 0, then you may have to also have a solution with x squared equal to 0 as an additional branch in some cases. But right now we'll just see where this takes us. The first thing that you obviously have to do is reduce the complexity of this, and that can be done by choosing another variable u to be y over x. That immediately gives us y equals u times x, and so we can almost get rid of the variable y altogether. How do we do that? Y prime is u prime x plus u using the product rule of differentiation. So I have essentially replaced y prime and y with simply u and x. So let me rewrite this whole differential equation. Left side is u prime x plus u, and the right side is u squared plus 1 over u. This might not seem to be drastically different than the original differential equation, but watch and see. This actually becomes very simple to solve. So u prime, it might make sense to move all the terms involving u to one side first. So what I'll do is I'll multiply both sides by u. So I get u prime x plus u squared equals u squared plus 1. Immediately you see that u squared cancels out, and I get u prime x equals 1. Now at this point I can take all terms involving x to the other side. There's only one term involving x, and that's this x multiplying u prime, so I'll take it to the other side. So I'm going to get u prime equals 1 over x. U prime is du by dx, so I can write that as u du by dx equals 1 over x. Now I do what's called separating the variables, moving all the x terms to one side and all the u terms to the other side. U terms are already on this side, so I won't do anything there. And that gives me dx over x. And now I integrate both sides. If I integrate both sides, this is going to be u squared over 2, and that's going to be natural log of x plus some constant, which I'm going to write as natural log of c, because then I can write this as natural log of cx, where c is some real constant. Now I can go back to the original variables, because u equals y over x, so I can put that here. So I'm going to get y squared over, I'll move the 2 over that side, y squared over x squared equals 2 ln cx. And what I can do is I can move the 2 inside, so I get ln c squared x squared, okay, and that gives me y squared equals x squared ln c squared x squared. So that's the solution of this differential equation. And because x squared is not 0, we don't have a problem here. You do have x squared as an argument of the natural logarithm, so you cannot have x squared equal to 0. In this manner, we have solved a differential equation completely. And if we have some initial condition, then that initial condition can be used to determine the constant c squared. Let me look at another example. I won't go through completely with this example, but I'll bring it to the form that I brought this to. And then the subsequent steps can be followed on your own by using one of my exercises in the weekly notes. But I just want to show you the initial steps involved in bringing it to that, massaging it to that shape. So suppose now we have y prime equals some linear function of x and y and another linear function of x and y. So immediately by looking at this, you know that you cannot employ this test, because if I try f of tx and ty, the 2 and the 4 will not obey the conditions of homogeneity. So you cannot write this anymore like this. So what you have to do now is to somehow find a change of coordinate systems so that you get rid of the 2 and the 4. And I show this in the notes in some detail, but basically you have to move to a different coordinate system known as zeta and eta. So the zeta and eta are just shifts of the xy coordinate system. So you're shifting your coordinate system. There's nothing else that you're doing. You're just shifting them. So one way to play this is to say that x equals zeta plus some quantity h and y equals eta plus k. And when you do this shift, you'll end up getting something like this. You'll end up getting zeta, and there's an h there, and eta, there's a k there. So you're going to get zeta plus eta plus h plus k minus 2. And then in the denominator, you're going to get negative zeta plus eta plus negative h plus k minus 4. All right? Now, what I'm going to do with this is you're going to demand that your shifts be of such form that h plus k minus 2 equal to 0 and negative h plus k minus 4 equal to 0. If all is well with the world, these are two straight lines in the hk plane, and they will have a unique point of intersection. You can actually find the point of intersection either by inspection or just by staring at this long enough. It's 3 and minus 1. You see, because 3 minus 1 is 2, 2 minus 2 is 0, and then 3, negative 3 minus 1 is, let's say, negative h equals, actually it's h equals negative 1 and k equals 3. Let's check that works out. Yep, now it works out. There it didn't matter, but here it does. So once you have this either by inspection or actually working it out, you then, all right, you found a coordinate transformation. The coordinate transformation is x equals zeta minus 1 and y equals eta plus 3. And this differential equation, once you have, so y prime dy by dx is just d eta by d zeta. Okay, so I'm going to get eta prime, where eta prime means d eta by d zeta, equals zeta plus eta over negative zeta plus eta. And now we are home free because this is homogeneous of order 0. If you put t zeta and t eta here, the t will come in the numerator and t will come in the denominator to cancel out. And now you can proceed as usual. You can call u equals eta over zeta. Well, first you have to do this step of dividing both sides by zeta. So I get 1 plus eta over zeta, negative 1 plus eta over zeta, and then you call u equals eta plus zeta, and then you proceed exactly as you did over there. So this is the shifting trick you have to prelude as a prelude to the full procedure that you had in the previous problem.